In a world where automation is doing so much more with databases, SQL tuning remains the domain of the human because it requires logical thought and some creativity. As a result, people think of it as a mystical art. But in this session, I'll show you 5 simple steps that hopefully can become a blueprint for you to follow when you're faced with tackling a SQL performance problem. I'm Connor McDonald. I'm a database advocate for Oracle. I love talking all things database, especially SQL and performance tuning. Simply scan the QR code or head over to linktree/Connor and you can get my Twitter, my blog, email, LinkedIn, Facebook, Instagram, podcast, YouTube, you name it. As you can tell, I love talking about technology. I said there were 5 simple steps to tuning SQL, so let's jump straight into step 1. Here's my first rule for tuning a SQL statement, and I think this might be the most important one of all. Step 1 to tuning SQL is don't tune the SQL. I bet you weren't expecting that. Now, don't click stop on the video now. Let me justify that statement with a moment. And to do that, I need to jump up on the soapbox. Now, if that's an unfamiliar phrase, it dates back to when speakers in public forums would jump on a soapbox to pontificate up to the masses, and I'm about to do a little bit of pontificating. My take is this: if you're tuning SQL, then you're doing it wrong. Now, let me justify that. You're naturally asking yourself, what? Here you are tuning into a SQL tuning talk, and the first thing you're being told is you should not be tuning SQL. So the question is why? Let me explain with a real example from a real customer I worked with many years ago before I joined Oracle. This was a retail customer, and as you'd expect, the data model had customers with 1 row per customer, plus a child table of transactions. New customers sign up, and when they buy something, they add a row to the transaction table. I won't reveal too much more to preserve anonymity, but we had hundreds of millions of transactions every single year. A requirement came in from the business saying, give us a report of the most recent transaction date for each customer. Now that's a very easy SQL statement to write. We simply do a max on the transaction timestamp from our customer transactions table, and we group by the customer account. This gave us a report like the one you can see here, 1 row for each customer with the most recent transaction details. There's no problems with the complexity of that SQL statement, but there was a problem when we ran it. And that problem was very simple. It's the famous hourglass. It took forever. It was fine in the early days, but as the volume of data grew, it got slower and slower. Thus, eventually the phone call that we all dread came in, and that's namely, please make it faster. We need this report every single day. And so began a series of attempts by us to tune this SQL. The first thing we tried is a time-honored technique, which I refer to as the Kiwi technique, and that is kill it with iron. If something is slow, then just whack a parallel hint on it, grab a bigger slice of the server pie. This indeed did make the query faster, but the lights went dim in the server room, the I/O subsystem got hammered, and generally everything else in the application bogged down while we smashed the database server to get this report done. So then we tried adding an index to just the columns we needed to scan this query. In that way, we could scan a thinner version of the table being just the index. That worked too, but when you're dealing with high transaction volumes like we were, every index has an overhead to the transaction response time. So we had a report that ran okay, but we added a performance penalty to every single transaction that we ever took from customers. So then we looked at partitioning the transaction table. Simply breaking a large table into smaller chunks does not by itself make queries faster, but we altered the report definition to show the last transaction only if that customer had had a transaction in the last 12 months. In that way, we were scanning just the report last 12 months of, in that way, we were scanning just the last 12 months of table data, and hence only 12 partitions of the table got scanned, no matter how large the table got. That worked. But in doing so, we had actually changed the function of the report. Now the report was somewhat vague when it came to customers who were not active in the last year because we did not have the transaction details for them. We had reduced the quality of the report, and we now had a partitioning license to pay for. More money for less functionality is never really a great sales pitch to your business representatives. To overcome that, we tried partial indexing on the partitions. And without going too much into specifics, we would combine our 12-month scan of recent customers and then do an index probe of the older data for those quiet customers to get the report back to how it was originally with all the customers now correctly represented. So we solved the issue, but at the price of a massive jump in complexity. The problem here is being so focused on tuning the SQL. And I get it. As IT practitioners, we love embracing our inner geekiness to solve problems just by looking at code. We all love that ego hit when someone sends an email saying, hey, Connor worked his magic on the code, and instead of 5 hours, it now runs in 5 seconds. Yet we feel like we have superpowers. But rather than adding parallel, adding partitioning, adding indexing, modifying the SQL, we should have done one simple thing, and that is go back to our business reps and clarify the requirement. Because when we did that, we discovered that the last transaction for all customers was really, we just have an interest in recent activity for customers. They just wanted to know who hadn't been to the website for a while, so we could offer them some sort of carrot, some sort of promo to come back and hopefully buy more stuff. So what was the solution we came up with? It wasn't parallelism, it wasn't indexes, it wasn't partitioning. We already had a modification timestamp column on the customer's table, which was used to enable optimistic locking. Each time a customer queried then updated some data, we would check the modification timestamp to see if the data was current or had become stale. And of course, the modification timestamp is a pretty damn good approximation of a customer actually logging on and using their account. They might not have bought something, but they're definitely in our system. So the SQL we ended up writing this report for became select account, modification timestamp, which became our approximation for the last usage time for that customer. And that's it. No more performance issues, no more complex code, no more scanning of those hundreds of millions of rows. And it's zero cost. No partitioning license, no complex code to worry about. But you only spot potential solutions like that if you don't focus on the SQL at hand. When solving performance problems, we need to step back from the laptop, step back from the code and look at the bigger picture. So to reiterate, step one is not the SQL that we're tuning. Now, if we're not SQL tuning, we are doing some tuning, obviously, but it's not this. It's this that we're trying to tune. I'm not saying we're tuning the user. What we're tuning is the user experience. Now, this might mean tuning SQL, but it might not be. A SQL that runs for 8 hours might be fine if it's only needed in the next day. It can run overnight. Conversely, a SQL that runs for 3 seconds might be the death knell for your application if that SQL needs to run in sub-second time because it's part of your millions of transactions. Let me share a slightly unpleasant experience that I think serves as a good metaphor for the rest of this SQL tuning presentation. A while back, I was pruning a tree and then fell onto an iron fence. Thankfully, my neighbors were there and they called an ambulance, but the paramedics didn't solve anything. They just wrapped a bandage around me and rushed me to hospital. I think of SQL tuning as like that ambulance. It's not really the cure, it's the triage process. What we're trying to do is just stop the bleeding and stop the pain for the customer. That's what stopping the bleeding is, until we can find a full cure. SQL tuning is just part of the treatment, not the entire treatment of a problem. So I'll jump off the soapbox now and continue on with my ambulance metaphor. Once the ambulance gets to hospital, the doctors are going to work on 3 things: finding the cause of the problem, then treating that problem, and then working toward a cure. Let's apply those 3 phases to the act of solving a SQL tuning problem. Step 2 is finding problematic SQL in your system. Anyone involved with SQL tuning typically has a query like this one in your toolkit. You narrow down your focus to a particular part of the application, such as payroll, and then you look for SQLs that are smashing either the CPU, buffer gets, running too many times, or hurting your I/O subsystem. But this is a bad place to look for SQL tuning because of latching. Latching is the way we control access to memory structures inside the Oracle database. It's a bit like using a public toilet. You latch the door to make sure that you're the only person using it at the same time. $SQL is a direct view into the memory structures of the running SQL in your system. In the database, if you access that structure, then you need latches to control access to that memory. But if you've grabbed a latch to look at $SQL, then you're hurting concurrent access to your system. What that means is you're hunting for SQLs that are bad with a SQL that's probably going to hurt your system. That's not a smart way. There's nothing worse than when you get called on to help with a SQL tuning problem and everyone noticing that the moment you've logged onto your system is everything is actually getting slower, not better. that's not a great way. It's like this story here. Make sure you don't pick the wrong leg. There is a better option than using $SQL. Since as long ago as 10G, there's a partner view to $SQL called $SQL Stats. Rather than having me explain why it's better, let me grab that reference straight out of the documentation. The column definitions for $SQL Stats are identical to $SQL. However, it is faster, more scalable, and has greater data retention. It's generally a better option. And because it's a separate memory structure from the real library cache, which is SQL, it's also designed that it can be queried quite aggressively without using latches. It's not the real library cache. So now you're using SQL Stats to find your problematic SQL. Once you've found it, it's time to move on to step 3. Step 3 is treating the symptoms. Let's assume this is the query we need to improve. We've got a table of vehicles with manufacturer details such as make and models, and I've got a simple SQL here looking for Honda Civics. But even though it looks simple, simple SQLs can be deceiving. No matter how simple a query looks, the first step is to determine whether it is actually as simple as it really appears. Here's a slightly different example. I'm querying something which I've called looks so innocent. But you can see from the consistent gets below, it's actually quite an expensive query. Inside the DBMS utility package, we have a cool routine called expand SQL text, which expands out all the components of a query to discover what the database will really see when it runs your SQL. In this case, looks so innocent is a view that joins DBA segments and all objects. They're both dictionary views as well, so it's a view of views. When we expand the SQL text fully using DBMS utility, we get this. But we're not done yet. There's more, and some more, and more, and more, and more, and more, and more, and more. And just when you think you're done, I've omitted the 16 more pages of that. So it's always worth checking. A short SQL in your app might be a monster for your database to handle. Once you've found the real SQL, the next step is where you want to check before tuning it is, does the SQL statement actually make sense? I've lost track of the number of times a slow SQL is simply slow because it is not actually correct. It doesn't meet the actual requirement. For example, here we have a query against the employee and department table, but something's missing. The join condition was forgotten. You might be thinking, but this would then return too many rows and it would be obviously wrong. But people often solve this by simply adding a distinct and they think, yep, everything's fine. But that's going to run very slowly because of the Cartesian product. Or similarly, this query looks fine until you realize that and takes precedence over or, which means in this query, we get all the rows that match the employee condition or the region condition or the tax condition, or every single row for which a subset is greater than 0. We needed to have some brackets in there around our or condition. Or this slightly less obvious one. This query looks fine, but you can see that there's actually no column called region in the subquery table. This query does not crash though with an error because region is actually taken from the parent table and becomes an always true subquery. This is another reason to always alias and reference your columns. If the SQL is indeed logically correct, the next step is to check the execution plan to see how the optimizer thought it should run the query. We're trying to see here if the optimizer made a bad decision somewhere in its process. Or, and I wanted to include this or because we often forget about it, it's quite possible that a slow SQL simply can't be made to run faster. Sometimes SQL tuning is just talking to the customer saying, look, you're trawling through 20 years of data to get a single grand total. It's a lot of work for the database to do. Sometimes just that explanation is all it needs to convince the customer that they should perhaps be a little bit more patient. But back to the optimizer. The way we check an optimizer's decision is to either look in $SQL plan, or we can just use DBMS XPlan display cursor, which will interrogate $SQL plan for us and give us a nicely formatted execution plan. But one thing that we should not use is explain plan command. Don't get me wrong, it's a useful tool for seeing perhaps roughly what the optimizer is going to do. But let me give you an example. Let me give you an example of why it's not as good as many people make out. Here's the execution plan for my query against the vehicles table that I showed before. We can see it's using the index presumably on the make column. My question to you is, now what? Is that a good plan? Is it a bad plan? We can't tell just by looking at the explain plan. It's not really doesn't really reveal enough information about whether a query is going to run good or not. When a doctor needs more information, they'll say, where does it hurt? And they'll sort of poke you and prod you and stuff. And we can do the same for a SQL statement. We can drill into whereabouts in the plan the optimizer either made a good decision or perhaps lost its way. The optimizer is a lot like a person. Let me explain. For human beings, cardinality is a really important thing. Now, I imagine you don't use the word cardinality in everyday life, so let me explain what I mean by cardinality. Sometimes I'll pop down the shop to grab a few things, and when I get to the checkout, I don't just go to the first checkout. I look along the whole line of aisles, and I look for the best one, and I scoot down to that one. In fact, there's one guy just in yellow there. There's only one guy. I'll queue up behind him. But sometimes I'll get there, and that one guy has got like the shopping trolley from hell. There's a million small things that he's going to go through the checkout with, and I'm like, oh no, I'm going to be here forever. And that's a problem. It's the same with the optimizer. It made a prediction or an estimate for each step in the plan that it thinks is best. If the actual results during runtime don't match that estimate, it's likely to be a bad plan. If it matches the estimate, it's likely to be a good plan. It's much like me going to the supermarket. If the guy in front of me didn't have many items because that was my prediction, then I'm going to have a good experience. And we can do this with the gather plan statistics hint with our SQL. When we run a statement with this hint, the database will record both the estimated plan by the optimizer and the actual runtime statistics as well. In our example, we can see that there are about 114,000 Honda Civics in our table. Using DBMS plan, we can see that the same 114,000 number in the A for actual row columns. But the optimizer estimated that in the E column, that there was actually only going to be 45,000 Hondas, that's the make index, of which only 25,000 were going to be Honda Civics. So the estimate didn't really match the actual result. So just like the supermarket, the result probably is not the optimal one. Putting our triage hat on again, sometimes we are just looking for quick fixes in order to get this SQL statement running. The optimizer chose an index because it expected far less rows than actually came out of the query. Perhaps a full table scan would have been a better option here. So we can use a hint for that. We've told the optimizer that we know better. In this case, I know Honda Civics sell really well where I live. There's 114,000 of them. So there's always going to be a lot. But I need to stress here, it works for this particular example, but when it comes to hints, I'm not saying that hints are the solution. As my good friend Maria Colgan often says, optimizer hints should only be used with extreme care. I often phrase this as the optimal number of hints in any application is 0. But remember, this is triage. We're looking for quick fixes until we can move toward coming up with a proper cure. If you're using hints for triage, try limit yourself to what I call the cool hints. Some examples of what I call cool hints are these ones. Each one is typically trying to offer the optimizer more information about the query. I just want the first rows, or this is the best table to start with. That's the leading hint. These are hints that are trying to assist the optimizer with its decision-making process because we might know more about the data than the optimizer does. Conversely, there are what I call the dangerous hints. The list of these hints is pretty simple. It's everything else. I'm not saying you should not use them, but ideally these are used sparingly. Because if we look at some of the common ones that are used, like full or index or force or join method, then in effect you are choosing to suppress the optimizer rather than assist it. You're limiting the number of decisions it's allowed to make. You're taking away options from its disposal. Now, as data changes over time, this suppression can lead to more performance errors. Maybe a plan should change over time, but you've told the optimizer it's not allowed to. As I said, hints are just a temporary fix. They're triage. We're trying to stop the bleeding. If you do use a hint as a temporary fix, here's a nifty trick to ensure that your fix is reasonably robust. Once you have the execution plan you need, by adding a few hints, use the plus outline format extension in DBMS plan. This will output a comprehensive set of hints that you can use to lock the plan you want into place. It's formatted in the correct hint syntax, so you simply just paste it into your SQL code and you're good to go. So now I've done some initial treatment, a bit of triage. Just like the hospital, I like to come up with something which is more permanent. It's time for step 4. I'm looking for the way that I can send my patient home fully cured. If you break an arm, you'll get sent home in a splint. It's the same with a problem SQL statement. Maybe you need not to fix the SQL, but just the periphery in order to let the SQL heal itself naturally. This often involves adding or removing indexes, and the key thing here is to make sure that you add or remove them safely. One of my favorite quotes about tackling problems comes from NASA, namely, "In space, there is no problem so bad that you can't make it worse." And it's the same with the database. Adding or removing indexes is a high-risk option because it could change the entire performance profile of many other SQL statements in your application. If you're altering indexes, then consider using the invisible indexes. To drop an index, make it invisible first, because if then you have problems, you can immediately reinstate it. If you're adding an index, also make it invisible and then use either session level or statement hints such that only your problem SQL that needed that index gets to use it. That way, you're limiting risk of regression elsewhere in your application. Since the optimizer is responsible for coming up with execution plans, sometimes all it needs is more or better statistics to help it on its way. Obviously, the first step is ensuring your stats are up to date and not stale, but we can do better than that. If we head back to our last example, then the standard statistics we get on make and model columns will not be sufficient to give us information about the relationship between the two columns. But for that, we can use extended statistics. It's another form of statistics we can add. Extended stats can be activated by using the DBMS stats API. The cryptic sys column you see is actually a hidden column that stores information about the make and model relationship. Because it's a column, we can then regather stats to pick up the fresh stats. Now when I rerun my query with the gather plan statistics, I can see that the optimizer now knows that we're going to get 114,000 Honda Civics. It has corrected its estimate, and as a result, it naturally chose the full table scan without me adding any hints. If you can't fix the SQL by fixing the periphery, then you might need to step in and help the optimizer by forcing a plan you want to use. But we're not talking about hints here. We're talking about something much better, which is SQL Plan Management, or SPM for short. This is a super cool facility that's been around for a long time, but I will admit, by the way, of a mea culpa, that maybe the terminology we use didn't leap off the page and shout SQL tuning. So I can understand people didn't really adopt it aggressively, but in reality, the feature is very simple. And if we strip off the terminology, it offers 3 things we strive for, namely, I like this plan, so please use it. I don't like this plan, so you're not allowed to use it. Or maybe over time that bad plan has become a good plan, so let's have another look. Let's look at it in action. Here's a standard SQL statement, and here's the plan the optimizer chose to run it with. Nothing out of the ordinary there. In SPM technology, we call that an accepted plan. This is a plan that can be used by this particular SQL. If you're not using SPM at all, then obviously every plan is an accepted plan. But when SPM is in play, then only plans that are accepted are allowed to be used. As we know, plans can change over time. The stats get updated, the data changes, etc. So each time we parse this SQL, we might get the same plan, or we might get a new plan. But with SPM, because we have an accepted plan, this new plan is not accepted by default. Even though we parsed it and the optimizer said, yes, is the new plan, this is the one I want to use, it will not use it. It will only use the accepted plan. The cool thing with SPM is we don't just throw it away, that plan that wasn't used. We save it, because this is the plan the optimizer now thought was the best plan, even though we didn't use it. And maybe over time it is better. Maybe the optimizer was right. Maybe the data's changed enough for that new plan to be the best plan. SPM doesn't mean I can only have one accepted plan. I can tell SPM to evolve a plan. This lets me tell the optimizer that this new plan is also accepted. The new plan, which we originally blocked from usage, now becomes an accepted plan as well. Each time we parse this query, the optimizer can come up with either of those plans and they'll be allowed to be used. If it comes up with a third brand new plan, it won't be allowed until we go look at it. We have this sort of very total control method of choosing which plans we want to allow the optimizer to pick. So let's wrap up this session on SQL tuning by reiterating. If you're tuning just SQL, then you're perhaps focusing on the wrong thing. Our aim as IT practitioners is to tune the user experience. Always remember, we build IT systems to solve the needs of those users. Speak to them, listen to them. They're the ones that drive the tuning approach. So thank you for your, look, hold on. I know what you're asking. Don't finish off yet, because what about step 5? Well, if you followed steps 1 through 4, hopefully step 5 is to sit back, relax, and just bask in the happiness and praise of your happy users because they've got fast running systems. You get to celebrate. So now it really is time to say thanks for watching, and feel free to connect with me on any of my social media channels. Bye for now, everyone.